Hello, everybody. My stream died for just a moment, but it should be back and we should be alive. I don't need that to be there. Okay. Just going to let this kind of warm up here a little bit, I guess. I'm not downloading anything. My stream connection says that it's good. So we'll go ahead and get started for the day. I made a little bit of an oopsie last class. I didn't save those notes that we took, but I didn't type very much, so I'll have to kind of redo that and upload those. But like I said, there wasn't too much of them, so we can kind of just recall about linked lists. And sometime today, hopefully, I will type up those notes again. But just a few reminders that next class is going to be a review session, and then the class after that is going to be the test. Now, I forgot to mention this, but I am going to, I did say this towards the beginning of the semester, kind of before midterm 1. I didn't require you to use Lockdown Browser for midterm 1, but I think I'm going to require you to do it for midterm 2. I will not make you use a webcam, okay, so you can like reference some notes. But I think I'm going to make you use Lockdown Browser for that second midterm, which is in a week. So I am assuming that you guys have downloaded Lockdown Browser for another class. I will have to provide you a UNLV link. So I'm going to try to find one of those links and send it to you by the weekend. And I'm also going to put up a mock midterm exam where you'll just have to type in your name just to test that the Lockdown Browser for you works, so we don't run into any problems during that day. Once again, no webcam is required, so if you take some notes, you can reference them. But the thing is, we're going to try to keep you off of the internet. So that's the goal for that. And if that upsets you, I'm sorry, but at least you don't have to use a webcam. So be prepared for that. If you have any concerns about that, please let me know. I will post some announcements in that link, like I said, anyway. So hopefully I can reach out to some of the students who are not in class today. So that's coming up next week. And this weekend I'll have a review sheet posted. On Monday we're going to go over that review sheet. So with all that being said, let's kind of talk a little bit about the linked lists. Actually, before I do that, I just want to let you know that Assignment 9 is posted. And I think I set the due date to be 10 days from now. Maybe longer than that. Nope, 10 days from now. With a late deadline of the 25th. April 24th is the due date of that. Please take a look at it. I hope it'll be fun. Oh, so Sibe asks about Assignment 9. What are the details in the terms of the easy way and the hard way thing? Okay, yeah, so let's talk about that today. And let's kind of use a little, probably a whiteboard for that. That's a great question. That's a great question. And today we're going to do some sorting on the singly linked list. So you're going to get some code for that assignment. As long as you pay attention, for the most part, you should get kind of the operator overload for the brackets, as well as maybe a sorting function. The swapping function, I'll probably do a version of it. I don't think I'll do the hard way for you, but I think I'll at least do something similar to the easy way. So we'll see how far we get on that today. So let me see what I can do here. There's one thing that I can't see here. Okay, so let's kind of do some linked list stuff. So I'm going to kind of copy some things in here. And so what CBay is talking about is in the assignment, there's probably the function that requires the most code is called swap or swap nodes. And so you have swapped nodes before. It's pretty easy because you're just switching the two elements that are in some array. Now when it comes to a linked list, the swapping can be kind of, it's a little more involved. And the reason for that is because of this next pointer here, and that we're kind of working with addresses. And so when it comes to swapping elements, if say we had to swap element 2 and element 3 here, and I'll use the whiteboard in just a moment, but I also have to let the head node here, I have to let it know that its next pointer is now pointing to this node, kind of thing. And so because we have these next pointers, the swap function is a little more involved than just switching them. So there's actually 3 ways that you can swap nodes in a linked list. There's actually 3 ways. Mainly 2 that will only work. There's only 2 of them that will work. And so I kind of mentioned those in the assignment. And so the easiest way to swap nodes is to actually just switch the elements within the nodes. This way you're not updating the next pointer at all. But there's kind of a caveat to that, and I also say you're not allowed to do that in the assignment. So there's like a super easy way to do the swap function. If you do the super easy way, your program will work as intended. So let's say you save this assignment till last minute, like many of you do, and you're really struggling to get the code done, and you just want the code to work, then you can kind of cop out and do this super easy swap method where you just switch the elements within that are inside the nodes, and you will get no credit for the swap function, though your code will work as expected. And at the end of that assignment, actually, let me pull it up here, I asked you guys a few questions. These are like some comprehension questions. We haven't done this before, but we're doing it now, and there's only 3 of them. And you're not expected to write any sort of paragraph. You're just expected to write 1 or 2 sentences, maybe, in a text file. And so I actually ask you a question about that, and maybe we can answer this question in class today. So if you come all the way down to the bottom of the assignment, you'll see that we've got some comprehension questions here. And so let's just read this one, and feel free to speak up if you'd like. So it says here that the swap cards function is supposed to only swap the next pointers and not the card within the node. Once again, when I say that, I'm talking about you're adjusting these green arrows here, and you're not touching the element inside the node. And so this may be annoying to code, which I'll discuss in a moment, but I'm asking you, can you explain an example of where swapping the next pointers will be significantly better than swapping the data within the node? In the case of this assignment, swapping the data within the node is probably not a big deal. But can you guys think of an example where if you were just trying to swap the data in the node, it would not be a good idea to do that? So I'll give you a few seconds to think about that. And let's kind of talk about the easy way and the hard way here. Can I make that bigger? Oops. All right, so that's okay. It's maybe a little gross, but it's not a big deal. Is anyone? Yeah, okay, so Red Rose kind of gets it, kind of nails it on the head there. And so I just want you to consider, what if the data structure is like a gigabyte? What if the data structure happens to be, 2 gigabytes? It's this giant data structure, and you have a linked list of it. And you're going to tell me that you're just going to swap the data within the nodes. Well, when you're swapping it, that takes a lot of kind of I/O. Or I/O maybe? Maybe not I/O, but it takes a lot of memory computation. And so you should definitely swap the next pointers in that case, because it will be so much faster. An address is only a certain amount of bytes, I don't know exactly off the top of my head. I should know that. And I mean, we could just print them out and look at it. But an address is significantly less memory than the actual node. So swapping the next pointers should be preferred in that case. So let's talk about the easy way and the hard way of this in linked lists. And so the easy way is only swapping adjacent nodes. Oh, gross. Sorry, I have some cat stuff going on in the background. Just want to make sure everyone's okay. And the hard way is swapping any nodes in the list. And so what do I mean by that? So when we're talking about this, when I talk about swapping adjacent nodes, T. Peter says I think address is only 32. Let's see. Pointers take up 4 bytes on 32-bit machines and 8 bytes on 64-bit machines. So 4 bytes is 4 times 8, which is 32 bits. Yeah, so 32 bits. You're kind of correct in that sense. So if I'm only swapping adjacent nodes, that means that I will only swap nodes that are right next to each other. So in this case, the easy way would be to, during your sort, you're only going to look at nodes that are right next to each other. And so are there any sorts that only swap adjacent nodes? Yes, there is bubble sort. You've seen bubble sort code before. And so bubble sort code only swaps j and j plus 1. So those are adjacent nodes. So it's either going to swap these two, or these two, or these two. But there are other sorting algorithms that will swap any node within the list. So when I'm kind of talking about the easy way to swap, there's a few things that you should consider. For one, you will only have to update 3 pointers. And so the pointers that get updated are, for one, the leftmost next, and then you have the rightmost next, and then you have the leftmost previous. And maybe I should put some hyphens in here so we kind of understand what I'm saying here. So what do I mean by that? Well, in this case of, kind of what we're looking at here, this square I've highlighted, the leftmost next pointer here will need an update, so that's this one. And then the rightmost next pointer will need an update, so that's this one. And then the previous to the leftmost. So this is the leftmost here. And so whatever element is behind this one will also need an update. In this case, this is the head node, so you'll have to update the head node instead. But that's still 3 pointers, right? And so in this case, it can be the head, maybe. So that's the easy way. Loaf is making tons of noise. You got to get out of here, cat. Wow. Lots of distractions today. So it's not simple by any means, but it's easier than the next way. And the next way is going to be the hard way of swapping nodes. So I'm actually going to maybe scroll down here a little bit. Maybe I can create some more space on this Microsoft Paint diagram. I would really appreciate that. Can we do that, please? How do we do that? I guess we'll do it that way then. Oh, I can do it here, I see. It's not very efficient. So the hard way of swapping nodes means I can swap any nodes in this list. And so it kind of comes down to a lot of cases here. So if we're going to swap any nodes, that means we can swap nodes that are adjacent. But it also means we can swap a node that's here and a node that's here. We can swap a node that's here and a node that's here. And so when it comes down to that, there's quite a few cases to consider. Let's see what I was talking about up here above. There's no scroll bar. I see. So we're at most 4 pointer updates. And so what does that mean? Well, that means, did I just mess this up? Of course I did. We're going to have the leftmost next, just like last time. The rightmost next, just like last time. The leftmost previous, just like last time. And what is the fourth one? I will ask you. What do you think the fourth pointer update is if we're swapping any nodes in this linked list? The rightmost previous, right? Linked lists are fun, aren't they? So this is kind of like the rightmost previous next and the leftmost previous next. And so let's kind of look at these one by one. So let's say I'm swapping, here I'll put like a little circle here. Let's say I'm swapping this one and I'm swapping this one. Let's not do that actually. Let's swap this one here and let's swap this one here. And remember that this guy's pointing at a null, probably. So if we're going to update the pointers, I'm going to mark them all. Let's give them some numbers here. So let's say that this is A, this is B, this is C, and this one is D. So the leftmost next, this is the leftmost pointer here in the array. So we have to update this one. So that's the A pointer. Let's see if I can put it in a better spot. So that's A. The rightmost next is going to be B. So this one actually has to be updated as well, right? Because the leftmost next pointer will be pointing to null now. And the rightmost next pointer will be pointing to whatever this element is. Then we have to update the leftmost previous next. So we take the leftmost previous next. So this is number C, this is letter C. And then the rightmost previous next, right? In the case of this update, it's now going to be pointing to this element here. And so then the rightmost previous next, we look at the rightmost, we go to its previous, and then we look at its next, and that's D. So do you see what I mean? And in the case of the leftmost previous next, that might be the head. But if nodes are adjacent, meaning you have to check for that. If they are right next to each other, only 3 updates. And it's going to be the same 3 updates that are up here. So I hope that you're sufficiently confused, because this is how crazy linked lists kind of get. And so you have 2 options, and I'll kind of explain to you why you might prefer to do one or the other. If you're going to do this easy way of swapping the nodes, I'll give you full credit. If you do the hard way, I'll give you some extra credit. So if you do the hard way, I'll give you extra credit. If you do the easy way, you'll get full credit. But if you pick one or the other, then your shuffle cards function is going to be a little bit different. So if you kind of come in here and take a look, shuffle deck will shuffle the cards all randomly. And so you're going to swap like 2 random cards in the deck. And so if you happen to do the easy way of swapping, then you can only shuffle cards that are right next to each other. So you'll just do a random swap, a random swap, a random swap. But if you did the hard way, the hard swap cards, then you can just get any 2 random cards in the deck and swap them. So that's what I mean. Today we're going to kind of go over this easy way of swapping cards. The hard way, I'm going to leave it up to you to use your brains to see if you can do that. But do you understand the difference? And if you don't, then maybe what questions do you have about that? And the main thing to consider here is, in the easy way, you just never have to consider the rightmost previous next. Perhaps I've scared you. Yeah. Well, please let me know if it doesn't make sense. Of course, I'm here to help you. And so let's kind of do some of that stuff. So I'm going to continue working off of this singly linked list that we were working on last time. And this one is what we use in the assignment anyway. So we'll kind of come back after the test to maybe look at doubly linked lists and perhaps circular linked lists. Though that material will be relatively similar to this material where we're looking at next nodes and stuff like that. So if you remember last time, this is the same code. I did upload this one to Web Campus, so you should have access to this code. And what we did was we kind of did a recursive print function as well as an iterative print function. I did a destructor kind of at the end. I had rushed that a little bit. But as you can see, I'm just kind of going through each node starting at the head. I'm saving whatever the head node was. I'm moving to the next node, and then I'm deleting that previous node. You need to do it in this order, because if you delete before you move to the next one, this is a huge mistake. If you do this, then, well, you're going to miss the head node, right? And if you do this, you're not going to have access to that head node anymore. This might work, actually, just letting you know, but you should not do it. If your destructor looks like this, notice that we did not set head equal to null pointer here. Right, if we did this, then this line of code would segfault. But we didn't do this. And so, in fact, we still have access to that original memory. And there's a chance that this will still work. But when you run Valgrind, it's going to tell you that you're probably doing invalid reads. And it should not be done. It should definitely not be done. If you recall earlier where I tried to segfault the program way back when we were first talking about pointers. I had deleted, say, a student object, and then I tried to access a variable that was within that object, such as the size, and that would cause a seg fault. So this may cause a seg fault, so please do not do that. You should do it only in this order. So that you kind of cover all of your bases, right? And so what we'll do is we'll save that node. We'll move to the next node before we lose it, and then we'll delete that previous node. And this is going to be all while the head is not equal to null pointer. All right, so we got a swap. We got a swap question here. Let's see what Red Rose says. So Red Rose asks, to check for adjacent nodes in the hard case, since it's a singly linked list, if you have cards A, B, C, D, E, it seems like you check if B is adjacent by just checking A's next address. But how would you check if B is adjacent to A if you're given B first? So kind of what you have to do in the swap, and we'll kind of talk about this, but let's kind of look at this UML here. Where is it? Okay. So notice here that the swap cards function actually takes two node addresses. It takes these two addresses. And so kind of at the beginning, what you should probably do is go through the linked list kind of node by node. And for every node, you're going to check to see if the node is equal to either of these. Yeah, you're just going to check to see if they're equal to either of these. And then the moment you find one, you know that it's going to be the leftmost. Awful asks, it is like swapping pointers. Yes, we're swapping pointers. In a way. But the thing is, it's a little difficult because it's not just enough to swap A and B here. We have to swap also kind of C and D. Just to swap two nodes, we need to update 4 pointers. It's kind of involved. It requires some coding acrobatics. Coding acrobatics, maybe. Yeah, and so I really haven't gone through this assignment, so no harm done, Red Rose. I appreciate the question, and I am sorry that I didn't show this UML, but you will have some parameters, right? You'll have some parameters. And like I said, today we'll get to one of these swap card functions, hopefully. And I'll do a version of it. You can do your own version. I expect you might, but... we also did a tail insert, right, where we just insert at the end. I think what we'll start with today is a head insert. And then maybe we'll do this swap and sort thing so that you guys are prepared for the assignment. And then we'll probably be done for the day. So let's go ahead and look at that. So let's do a head insert. So instead of inserting the element to the tail of the linked list, we're going to put it just at the head. So this one might look like void head insert. It's going to take a type item. Let's see what that is. Looks like it's type 1 element. And so this one will be very simple. So just like with any linked list, if we're inserting something, we have to allocate. So step 1, we got to allocate the node. So we'll do that. So we're going to say node pointer new element is equal to new node. And then inside that new element, we're going to assign the data to contain this element pointer. And then we're also going to assign the new element next. This is good practice, okay? So you should always do this to be equal to null pointer. Because if the head node happens to be null, then we won't have to update this next pointer at all, and we guarantee, ensure that the linked list will have null at the end. It's very important. We're going to ensure that it will have null at the end of it. Okay. And so once we do that, now we can just insert it. Now this is going to be a super easy insert. The first thing we have to check for to see if there's already a list, right? We kind of did this already with the tail insert, right? So we'll do the same thing. So we'll say, hey, is the head equal to our null pointer? And if it is, then we can just say head equals new element, right? Some of you guys also might just want to call tail insert. That would work as well. Except the fact that I had already allocated this. So if I did that, I would have to delete the node. So let's not go that far. That's just me being goofy. Okay. So if there's not a list, we'll just insert it as the head. And then for those of you who are good coders, you might say that this is now equal to null pointer, just to avoid that potential alias, right? Just to avoid that potential alias. But if the head is not null pointer, then this is going to be, well, I kind of just, we'll do it this way, but we can simplify this. Else, there's already a list, and so we can actually just say that new element next equals the head, and then we can say that the head equals the new element. And I'll tell you this function is similar to add card to deck or whatever it's called. Let's go take a look. Add to top of deck. Okay, so this is kind of like inserting the head node to a linked list. Now, actually, we can simplify this, and the reason for that is if head is already equal to null pointer, if head is already equal to null pointer, then we actually don't need to do this check. So my apologies on that one. If you notice in the... Yeah, let's really simplify this out. This is probably the simplest insert there is. And let's also increase our size, since we are keeping track of that. But if we come back up here and look in our constructor, you'll notice that I already initialized head to null pointer. And since we're inserting this head, we can ensure that the new element next will be assigned to null pointer, given that head is equal to null pointer. So I'm sorry if I was a little bit confusing there, but this is actually the simplest that it can get. So hopefully I didn't mess anybody up here. Please let me know if that confuses you. Notice here, though, that the head insert is very much simpler than the tail insert, in which the tail insert, we kind of have to loop through these elements, and we do have to check to see if the head is null pointer before we attempt to loop through. This one is very simple. And so let's kind of do some tests here. Let's do a head insert instead. And so this, in fact, should reverse the list, right? So initially with a tail insert, we saw 1, 2, 3. With the head insert, we should probably see a 3, 2, 1. Based on the lack of questioning there, I assume I didn't really lose you guys too much on that one. We're banking on that. Hopefully things went well. And the next thing we'll do is we'll do this bracket overload. The bracket overload is super helpful. And in fact, it will make this program a lot easier. Now, I will tell you that the bracket overload is not the most efficient way to code a linked list. Someone might tell you that. If the linked list is going to remain relatively small, I will not be complaining. But if your linked list is going to happen to have maybe over 1 million elements, then the bracket operator will definitely not be the most efficient way to do this. And you'll see what I mean. I'll explain that. All right. Oh, also, I think most of you guys figured out this -O thing. But -O just means you can rename your object code. So as I said, if I put -O and I type sandwiches, it's not main. It will actually rename this to sandwiches. And so if I refresh, I actually now have a file called sandwiches in here. And when I run it, I can say sandwiches. We'll just do iteration. It doesn't really matter, but you can see here that it went in reverse order, right? Because we were inserting on the head of the linked list and not on the tail of the linked list. Similarly, I could insert in the middle of the linked list if I want to. That's kind of what's nice about linked lists. And in fact, you can maintain a sorted linked list by inserting elements into it and keeping them sorted on the insert. So as opposed to maybe a head insert or a tail insert, you might have a sorted insert. But let's go ahead and get to this bracket overload. So let's say somewhere down here I want to access the SLL item element located at 3. Notice that this is red, and that's because we haven't overloaded the bracket. But I just want this to operate the exact same way that our paint diagram might here. So in this case, if I wanted to access the third element, I would definitely want that bracket operator to return the element located within this node, right? Because this is 1, 2, and 3. Or if we're talking about indexes, this is 0th index, this is the first index, and this is index number 2. So this one's kind of fun. And so we'll actually just put it right here. And so I'll change this one up a little bit from the assignment so that you guys actually have to do a little bit of work. In the assignment, let's look at it. Notice here's the operator overload for bracket. Notice it actually returns a node pointer instead of a card. This returns a node pointer instead of a card. The reason for that is so you can use this operator in maybe your swap function. This bracket might make your life really easy in the code. As long as it works correctly, you won't get marked, right? So that's kind of why this is returning the node, so you have access to that address. If it was returning the card, then you wouldn't have access to the next pointer, for example. In this case, we're just going to return the element within the node here. So we'll return whatever this type 1 data is. I will say notice also that this operator is private, which means in main I wouldn't have access to that address, and that's by design, right? If this happened to be public and somewhere in main I just pulled out an address from the linked list, and I was like, I can do whatever I want with this. I could break my code. So this is private by design. But in the case of this program, since we're only going to return the element and not the entire node, let's go ahead and make it public. Let's go ahead and make that operator public. So this operator will return a type 1, whatever that be, maybe an int, maybe it's a character, maybe it's a card. And it will be an operator overload for the bracket, and it's going to take an int index. All right, let's do some checking. Let's do some fun checking. So let's say if maybe our index is less than 0, or what if our index happens to be greater than or equal to our size? I want to make sure I'm using the correct size. Yes, I am. Right, so just like in any array, let's make sure that our index is not going to go out of bounds. We could maybe print out some error message. Indexing error, operator, bracket, right? Maybe we'll do SLL. And then let's just return null. Maybe not null. Maybe we can just do an exit. Right, this is a runtime error. It's okay to exit here because this is an error. Some functionality error going on there. Else, we know that our index is in the scope. So we need to traverse this list and go to the node that's in the list, right? So if we look at our paint diagram here, let's say I wanted to return the third element. I'm going to have to go from this node to this node to this node. If the index happens to be 0, then we're going to stay at this node. And if, of course, the index happens to be 1, we're going to move once. So let's kind of code our way so we can get some of that functionality. And so we're going to have to traverse the node. So let's start with a traversal node. And let's set it equal to the head of the list. And then we can just do maybe a for loop, right? Let's do maybe a for loop. For int I is equal to 0. I'm getting ahead of myself here. I is less than the size of our linked list in I++. We can say that the traversal node is equal to the traversal node next. And at the very end, we can return the traversal node data. Red Rose asks, the doubly linked list would be more efficient for the bracket element since you have to go to at max 50% of the list. Well, I wouldn't say that necessarily. Unless you already had maybe a pointer looking at that index. What I would say, and I'll explain it when we get to the sort function today, but the doubly linked list would be so much better for sorting because we directly have access to that previous node. And in the case of this one, we don't have access to the previous node from this element. Say we're looking at this element. There's no way to get back to this element. And so when it comes to sorting this list, we kind of have to go through the list and then... So say I'm using brackets, right? If I do a bubble sort, and I'll show you what I mean, and I say let's swap elements 3 and 4, or I guess index 2 and 3, if I want to swap these, inside of a for loop, I'm going to have to say, all right, I'm at I equals 2, use bracket operator. And then we're going to go down this way, and then we got to save it. And then we got to go to 3. So then we got to go down, 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 3. And then once we're there, we have to actually swap them. So when we're in the swap, we're going to traverse the list again to get to this element. We're going to traverse the list to get to this element. We're going to traverse the list to get to this element. And so the point I'm trying to make is we end up traversing this list a ton of times, especially when we use a bracket operator. So kind of like if I have a bubble sort, I've got this hidden while loop that's inside. Here's another for loop. So I've actually got a triple for, right? If we're swapping, I've got a for, oh god. And I've got a for, and then the bracket operator incurs another for. And if I call the bracket loop twice, I've got like a 4 times 2 here. So it's like 4, 4, 4, 4. And so that's kind of what I mean, that the bracket operator, just in general, is pretty inefficient for linked lists. With the doubly linked list, it would be more efficient to sort. I'm not sure how we could implement the bracket operator to be more efficient with a doubly linked list. Other than that, we could go both ways on the list. So maybe we'll have to sit and think about that one for a little bit. But for now, I'm just going to convince you that this bracket operator works. You're welcome. So if our index happens to be 0, then we'll look at the head node, and then we check to see if 0 is less than 0. It's not true, so we actually skip this for loop, and then we return the head node's data. If the index happens to be 1, we'll traverse 1 to the right, and then return the data. If the index happens to be 2, then we will... Oh, this is wrong. This is wrong, guys. I'm sorry. I'm glad that we stopped to talk about it. We're going to do the index, right? Do the index, not the size, the index. If the index happens to be 2, then I will be 0, traverse. I will be 1, traverse. And then this for loop ends, and then we're going to return that data, right? So it looks like this bracket operator is going to work. So, then I guess we'll just kind of test to see if it works down here. Oh, we got an indexing error. Why did I get an indexing error? Well, in fact, I tried to index it at 3. That's not correct. Let's index it at 2 instead. Right? The size of that linked list is 3. So I can only index it at 0, 1, and 2. See, I just saved myself. There we go. So it happens that 1 is at the end of that linked list, right? We know that for a fact because we did some head inserts. 1 happens to be at index number 2, so you can see that the bracket operator returns what it should. So now let's kind of do a sort and a swap. So this is where things get fun. So we're kind of just going to have to wing this, and I just want you to have some code available. Now, as I said before, this operator in the assignment is returning a node, and that helps me with the swap, and it helps me with the sorting function. Since I chose that this operator is not going to do that, I'm going to make a private function that does just what I'm talking about. So let's say we get node, and we're going to say like maybe okay, so this will be almost exactly like the bracket operator, but for nodes. And this will help us with our sorts. Okay, so I'm actually going to copy this exact code. It can be exactly the same. Except in this case, instead of returning the data, we're going to return the actual node. Okay, so there's that. And now we can begin sorting and swapping. So let's kind of put those somewhere in our code as well. So the first thing that we're going to want is maybe a void swap. And this swap maybe can take ints or nodes. Let's go ahead and do the node since that's the way it is in the assignment. Node B. And let's go ahead and make a sort function. So I'm going to do a standard bubble sort, and I'll show you why this makes it easy. The bracket operator. So standard bubble sort is this. Bubble sort is an inefficient sorting algorithm, by the way, for those of you that didn't know that. And when you get to maybe CS 302, you will learn about more efficient sorting algorithms. But bubble sort is kind of what we're just going to work with now. Another reason to use bubble sort is bubble sort swaps adjacent nodes. And so what we'll check is if perhaps get node at located J, and we want to know if its data is, say, maybe less than the node located at J plus 1. Then we'll swap those nodes. Now I'm going to kind of explain why I'm allowed to do this. And then I kind of want you to think about this on your own. And in the assignment, you're very welcome to do this if you'd like. If you'd like to try to sort the list without using a bracket operator or a function equivalent, you are going to have to do some major stuff here. You're going to have to maybe make a node traverse, 1 and a node traverse 2. And in your code here, you're going to have to, go to the next node, go to the next node, reset a node, go to the next node. Do you know what I mean by that? And so when it comes to sorting the linked list, this kind of bracket operator really helps us out. But as I was saying before to Red Rose, this is very inefficient because I've got a for loop here and a for loop here. Now, for you complexity guys out there, that's already n squared. And then I call get node at. So if I come up here, that has a complexity of almost n. And then I call get node at again, which is also complexity n. But they're kind of side by side. They're not nested within each other. So the complexity of this is, and you don't have to know this, okay? I'm just kind of talking out of my computer science head here. But up to this point, your complexity is like 3 times n to the third, which all I'm saying is if your linked list is over 1 million elements, you're going to be waiting a while for the list to sort. You know what I mean? And then if they happen to be true, you're going to call get node at again and get node at again. So this becomes like 5 times n to the third. And so this sorting algorithm is very inefficient, especially since we're using this function. I just want you to be aware of that. But for the purpose of our assignment, it will make our life easy. So now we're going to do the swap function. We've got about 20 minutes left, so we're going to do our best to kind of get that through. So let's just kind of talk about some of the stuff that we got going on here. And we're just going to kind of speed through this. And please let me know if you're confused or if you have any questions up till this point. This code is going up on Web Campus, so you're welcome to reference it. And it's almost identical to the other assignment, okay? You're going to have to kind of think about it, where you have to replace code and names and stuff, but that's the point, right? I can't just outright give you the code. I can give you similar code, and you can kind of work with it from there. And if you're going to be doing the hard swap, then you're going to have to work it out yourself anyway. So first, let's identify our left and right nodes. So if we look at my paint diagram here, I would like to identify my leftmost and my rightmost nodes. So I'm just going to make some kind of temporary nodes, left and right. I have to bring the pointer over to that one as well. And then we're going to kind of just go through this list here. So I'm going to say maybe node. This can just be a temp node for now. And we're going to say that it's equal to the head of the list, right? So this is our traversal node, but I'm naming it differently because I'm going to use it kind of for a different purpose later. This is our traversal node. And so all I'll do is while our temp does not equal null. And there's a few other things that we can check for here just to make sure. Let's do this first. If A equals B, then it's the same node, right? So let's just return no swapping to be done here. Else, if we're swapping two nodes, then it happens that there's at least two elements in the list. And so we'll just say if our temp is equal to A, we can say maybe that the leftmost node is equal to A. And then we're swapping adjacent nodes. Recall this, right? So what is the rightmost node? Let me ask you guys. What is the rightmost node in this case? If left happens to be A, say in this case left happens to be A, which one is B? Do I have to traverse any more? I know that these elements are adjacent. Yeah, it's A next, right? So, I mean, really, I could just say B here, right? Or I can say right equals A next. They're exactly the same. This is B. And then we'll break, kind of. We'll do an else if. Temp is equal to B, then we're just going to do the opposite, right? So our left will be B, and then our right one will be B next. This is A. All right? And then we can break. And then at the end, right, we don't want to iterate off into oblivion. So we have to move it forward. Right? So what does this do? This identifies now there's actually something else I can do in here, right? I can try to identify what is the leftmost node, right? But I'm not going to do that. I will leave that for you to do. If you want to make this more efficient, you can do that in your assignment. What I'm saying is that you can identify what the left previous is also in the same while loop, right? So if this is A and this is B, then you can also identify this node while you're traversing. You can also identify if the node happens to be the head node. So I'm going to leave that up to you if you want. In this case, I'm going to bring out another while loop. We say, what is the left previous? So we're going to do a few if statements. We're going to say if head equals the leftmost node, then I'm going to say temp is equal to null. So that's just going to tell me that there is no left previous because it's the head, right? The leftmost is the head. Else, let's kind of do this temp equals head thing again. Then we'll say while our temp does not equal null pointer. I got to make sure I'm being consistent here. I think that null and null pointer are equal to the same thing, but it would bother me. think I have a little bit OCD. Not to say I do, right? For those of you that actually have OCD, I'm not trying to be offensive. I just like to be consistent, that's all. Else, left is not the head node, right? Left is not the head node. And so what are we going to check for in here? Well, let's say maybe if temp next equals left. If that's true, let's break out. Temp is on the left previous, right? Because we found it. Else, if it's not, right, then we're just going to move temp to look at the next node. As you can see, this swap function is getting kind of out of hand, right? So in the assignment, I did kind of say that this function is probably the worst one. Maybe I didn't say that, but obviously it has the most detail, right? Because I'm trying to explain to you this process, right? I'm trying to add all my comments here as well. So we've identified the left and the right, and then we check to see if the head is equal to the left. If it is, we're going to say, hey, temp is equal to null pointer. If head is not the leftmost pointer, or the leftmost node, then we're going to iterate through one by one and look for that leftmost node here. So we'll say, hey, temp starts at the head, while temp is not equal to the null pointer. If temp next equals left, then we'll break out, because we know temp is looking at that null pointer, or it's looking at that leftmost, right? So if this is the left node, temp will look at this, it will say, hey, is next equal to it? Nope. So then it will move here, and then we'll say, hey, is next equal to this one? Yes, it is. So then it will break out, and temp will just be looking right at this node here. And so that should get us our leftmost node. And so now we have to swap. Swap pointers. So there's 3 of them, right? Let's do the left next. And we're going to have to do some temp stuff. So I'm actually going to even pull out another node, temp swap. And so the first thing we'll do is we'll save the leftmost, right? So let's say that temp swap is equal to the left next. So we'll save it. And then we'll say that the left next equals to the right next. Well, actually, here's where it gets fun. Let's kind of look at our whiteboard and try to work this out. If I do the left next, it's going to be equal to the right next, right? So in this case, it'll be equal to null pointer. But then the right next is going to be equal to left. So I actually don't know if we need to save that. Let's kind of not do this yet. So left next equals to the right next, and then we'll just say the right next is equal to left, right? So this is leftmost next. I said that already. And then we'll do the rightmost next. And then we'll check the leftmost previous next. So I checked temp, right? Temp supposedly contains this value. So if temp equals null pointer, what does that mean? That means that the leftmost is the head node, right? So if temp is null pointer, then the leftmost previous, or the left node, is the head pointer. And so the head now equals right, right? Else, all we have to say is temp next equals right. And that's it. What do you guys think about that? Was that fun? All what, line 135 to line 182? Did we have a good time with the easy swap function? So hopefully you kind of see what's going on here. You have some opportunity to make this better, right? You could kind of put this block of code somewhere up here in this while loop. Speed running swap function. Yes, that's what we did. You can kind of make this more efficient by putting it up here. Alternatively, and take a note here, okay? So I won't mark you for this. If you want to pass in the indexes, and well, no, don't do that. So the swap will have to take the nodes still, but you could also kind of just iterate through the list, identify what indexes they're at, and then use the bracket operator at index -1. Do you know what I mean? You could kind of save what the indexes are, and then you don't have to identify this left previous and this right previous, because you could just take the leftmost index -1 and the rightmost index -1. So you have a lot of options. That's what I'm saying. I hope that this kind of helps you get started. We're going to verify that it works first before I send you on your way with this linked list madness. And I know that you might have questions, but you're not sure what question you should ask. But if you have any confusion, please do your best to let me know so we can kind of talk about it. Because I know that was probably insane. Probably not very fun to watch. Probably not very interesting to watch. But let's make some list here. Okay, so that looks like an unsorted list. Let's maybe print it. Let's maybe sort that list. And let's maybe print that list again. Let's see if we actually sorted it. Recall this is the easy one because of their adjacent. And so notice I'm only swapping J and J+1. Let's give it a shot. Let's give it a shot. By golly, I hope this works. Because linked lists are probably the most insane thing that we've done all semester. It compiled. One. All right, so that's our unsorted list. We did it. Isn't that crazy? Wow, that was fun. Let's run Valgrind. Let's run Valgrind with this to make sure. Let's also spell sandwiches right. To make sure I didn't lose any memory. All heap blocks were freed, right? So I didn't lose any nodes or anything like that. So it looks like we did it. Okay. So with that, you probably have enough knowledge to complete assignment 9 in its entirety. So let's maybe just take a moment to look at it. We've got 4 minutes left. And you can ask any questions that you'd like. I made a video on it. The video is pretty long. I'm sorry about that. But maybe we can just kind of look at a few things in here. So just so you know, this is the deck. That's not the deck class. Let's make this a little wider. So this is the deck class here. Oh, let's see. Sibe says, the thing I'm confused about is how you get the previous leftmost value, because didn't you say SLL can only go forward and not backwards? Yes, I did. So let's go look at that. And that's exactly what I said. So I kind of have to iterate from the head multiple times. That's what's going on there. So if we look in the swap, so the first thing I do is do that check. And then I first identify the left and the right. So notice that I say that the temp here is equal to the head. So starting from the head node, I will go right on that linked list in one direction until I either find the leftmost, well, until I find the leftmost node, whether it happens to be A or B. And so once I find it, then I save them, right? I say left is A and then right is B, or left is B and right is A. And then look what I do. I start over. So I say, hey, is head equal to the left node? Is head equal to the left node? If it is, then I'm just gonna say, hey, temp is null. But notice here, I'm going through the list again from the start. So that's kind of what I'm explaining to you, is that I reassign temp to start at the beginning of the list again, and then we start all over again, right? And then I go one by one looking for temp next. So yeah, that's how I did that. It's pretty inefficient. Red Rose asks how we would do this with recursion. That is 100% a possibility. Right, so Red Rose asks if up here temp next equals A. Yeah, so you could do that check in here, right? But you might have to have another if statement to save for the head node, right? You'd have to check that head node first before you kind of put that line of code in this while loop. If you're going to do this recursively, you have options. I would say the doubly linked list would be much better for a recursive implementation of this. But recursively, you would have to swap. Maybe we can do that next time. That would be kind of involved. It would just require some thoughts, you know, some knowledge, some thinking power. We could do it, though, for sure. So quickly, I don't want to hold you too long. The deck class is nothing crazy, okay? You've all done this stuff before. It has nothing to do with the linked lists. All of the code in the deck class is easy peasy. I've done this before. Okay, so you're just going to do that. And once that's done, then you kind of have to go through all of this stuff. The default deck constructor kind of looks like the same one we did for our singly linked list. Clear deck kind of looks like our destructor. Our destructor looks like our destructor. The assignment operator is going to be fun. That might require some code because you're going to have to deep copy the linked list. So you're going to have to allocate the same amount of nodes on the left side as you will on that are on the right side. The copy constructor will be easy, right? Because you can just use the assignment operator overload. The bracket operator I already kind of did. Add to top of deck I already kind of did. Remove top card, I'll leave that one for you. These are easy. Those are all easy. Swap cards we talked about. Sort deck we talked about. Shuffle deck I'll leave for you to figure out, though you can always ask me questions. So we kind of covered most of the assignment today. You can totally do it at your discretion. So with that, that's the end of class. And I'm going to send you guys on your way. So if you guys got some questions for me, please let me know. I'll be available in office hours in 15 minutes or so. Thanks for coming to my TED Talk. Thanks for coming to the linked list madness today. This code will go up on Web Campus. This recording will go up on YouTube. I will retype out our notes. This whiteboard will also go up on Web Campus. And everyone will be happy. So with that, I will see you guys next time. Also, be looking out for my announcements, right? Because I'll be sending a few sometime before the weekend. Whoops. There we go.